Okay, on Friday's class we were talking about a curious electromagnetic detour, and we remembered about permeability of free space was mu O, and we talked about Ampere's law, that its real form looked like this. We used it to derive the form that we were using earlier for figuring out the strength of the magnetic field, some distance from a current carrying wire. And then we said it works for more complicated cases too, where there's an infinite number or infinitesimal short segments, and you got to get into calculus. Okay, but then I showed you one for finding the equation using Ampere's general formula law to find an equation for the magnetic field inside the core of inside a solenoid that has no core. So I attempted here to draw a solenoid that has no core. Okay, and we had derived the equation when the bell rang. We were at, I think we were somewhere about like B delta L, maybe cos theta, was equal to the mu I, and I hadn't talked about n. Okay, so we had gotten rid of all the other terms because the B was 0 because it was so far away, and the others, the angle was 90 degrees. So we said, okay, it's going to be B, and the delta L is really just the length of the solenoid. So this is L. And the cos theta is going to be 1 because the angle is 0. And that's equal to mu. But now the current, like this would be true if there was just one coil, one wrap. But there's going to be a whole bunch of wraps in this solenoid. So the field obviously is dependent upon the number of wraps times the current in each one. And so to get our expression for B, it's going to be mu O capital Ni over L. But people don't really like leaving it like this, so they tend to say, well, let capital NL be just equal to little n. So capital N is the number of wraps of the solenoid, the number of wraps of the wire in the solenoid. And L is the length of the wire. And so what little n is then, it's the number of wraps per meter. And so most often we write it as mu O and small n I. And then on the side we say where little n is equal to capital N over L. The units here will be per meter, right? Because the number of wraps won't have a unit, but the L will. So it'll be 1 over meters in the equation. But in most questions, they give you the capital N and the L so that you can find a little n first. So I asked you over the weekend then to do the 4 questions on this half sheet, okay, of a solenoid. So let's just take a look at them. You have the answers there. Oh, wait, there was one other thing that I should have talked about. On your page, there's an example, but then it also talks about the fact that mu without the O is magnetic permeability, just not of free space. So if we put a core inside our solenoid instead of empty space, then the mu will be the magnetic permeability of that material. So if we put a ferromagnetic core in there, the mu for ferromagnetic materials is a lot bigger than the mu O. So it would be different for iron than it would be for copper or whatever, but it's much bigger, which is what makes then the magnetic field bigger, right? If the mu is bigger than mu O, then the B will be bigger than what it would be if there was no core. There are other materials where the mu is really close to the mu O, and then there are materials where it would be less. So this equation is if there's no core in the solenoid. If there is a core in the solenoid, it's just mu Ni, where the mu is the permeability of that material. Okay? So if we go to this page then, the 4 questions. Number 1, a solenoid with no core has a length, so there's the edge of my page. So it has a length of 25 centimeters, which of course you're going to change. It has 400 turns. So N is 4, capital N is 400. Magnetic field strength, B, is 0.26 Teslas. Inside the solenoid, what must the current be? What is I? So you might want to do first step, little n is equal to capital over L. So 400 over 0.25 of a meter. Okay, and so you should get, that's what, 16, a quarter? Yeah, 1600 meters to the negative 1. Okay, and so then go to B is equal to mu O n I. So I is equal to B over mu O times N. So 0.26 Teslas, 4 pi times 10 to the negative 7 Tesla meters per amp. And then that's going to be times our 16,000 newtons to the negative 1. Now, you have to be careful. You can't type the 4 pi to the negative 7 in your calculator. It won't let you. So instead, do 4 times 10 to the negative 7, 4x exp 7, times pi, times the 16,000. And then whatever you get, divide that into the 0.26. Okay, and when you do, you should get 129.3 amps for number 1. Number 2, an air-filled solenoid. So again, it's going to be mu O. Has a length, so again L, 42 centimeters, so 0.42 of a meter. There's current of 3.2 amps flowing in it, and the field strength, B, is 1.2 Teslas. How many turns of wire must there be in the solenoid? So you're looking for capital N. First you'll find little n. So B is equal to mu O little n I. So little n is equal to B over mu O I. So 1.2 Teslas, 4 times 10 to the negative 7 Tesla meters per amp. And you're going to multiply that by your 3.2 amps. And again, be careful. Whoops, I lost the pi. Be careful typing your 4 pi in. So do 4 exp negative 7 times pi. And when you do, you get a little n of 298,415.52 meters to the negative 1. So then you say, okay, little n is equal to big N over L, so big N is equal to little n times L. So that 298,415.52 meters to the negative 1, and you're going to multiply that by 0.42 meters. Okay? And when you do, you should get 125,334.5 turns. Okay? Answer number 2. Number 3 says a solenoid has a core whose permeability is 9.42 times 10 to the negative 4 Tesla meters per amp. So this time it's not empty space, it has a core. There are 380 turns, so capital N is 380. Its length, L, is 36 centimeters, or 0.36 meters. If there is 3 amps of current, I is 3 amps of current, flowing in the wire, how strong must the magnetic field be inside the solenoid? You're looking for capital B. Okay, so you could find your little n first, capital N over L. So take your 380 and divide it by 0.36 and get 1,055 I think it might be 5 repeating, meters to the negative 1. Okay? And then do B is equal to mu n I. So B is equal to